chapter 5.2, linear quadratic systems. And what we're going to be doing is something similar to what you did when you just did the pure linear systems, is solving for the point of intersection where the x's and y's are the same for the graph. So we can have a quadratic, and we can have a linear equation cutting through it, and we can have two solutions here, a different set of x's and y's, because remember when we do the quadratic, we have that plus or minus on the root. Sometimes it could be tangent and have one solution, or you can have no solution. That means we have a line that is not going to intersect the parabola at all. So what I have here is I set up one with should have a solution here, and we have different options on how to solve this. But what I'm going to do is I'm just going ahead and solve for y for both and use substitution. I can just solve for y for this one and put it in for the x. I mean for this y, but I'll go ahead and solve for y on both. So we got y is equal to 4x plus 3, and we have y is equal to x minus 2 squared, and that's going to be a plus 11 right there. So I'm going to set these two equal to each other. I'm going to set this equal to that because these y's are the same on my graph if they do intersect. So we have x minus 2 squared plus 11 is equal to 4x plus 3. So I got a brand new quadratic that I'm going to solve, so I just want to go ahead and get this x's all to one side and a 0 to the other. That's x squared minus 4x plus 4 plus 11 minus 4x minus 3 is equal to 0. So that's going to be x squared minus 8x, right? That's 15 minus 3, so that's going to be a 12, right? Yeah, plus 12 is equal to 0. That it can be factorable. That is a negative 6 and a negative 2. Well, that just makes it real nice and hunky-dory. Sometimes they're not factorable, but still solvable. And what you would do, say if you had like a 4 plus or minus radical 3, you would still substitute that 4 plus or minus radical 3 one at a time in here for this x, and then clean it up, and you would have maybe like 7 plus or minus radical 3 or whatever. Or a 7 plus radical 3 and a negative whatever. Okay? So we have this, and we of course have x is equal to 6 and x is equal to 2. Yippee-yay. So let's just plug this 6 and this 2 back into our equations. You can plug it in right here, or you can plug it right here. I tend to be on the lazier side. So like here, I got 24, 27. So I have a coordinate 6, 27. And when I plug in my 2, I have 8, 11. So we can have 2, 11. All right. These are my two solutions. Now, you're going to get an option of using this calculator. Now, there's a reason why a lot of schools don't allow the Casio calculator, and here's one of them. So we can do this. I already inputted the equations into the graph, and of course, solve for y. That's one reason why I did it over here. I'll go ahead and draw. And when you initially have it, remember your V window could be standard, and you're not going to quite see it, so you can just kind of zoom out. And once you zoom out, you see where it crosses the parabola twice. You just want to G-solve it. G-solve it, and we're going to look for our intersections. And it's going to give you one at a time. 2, 11, and 6, 27. Again, this is just for, it doesn't improve your brain that much, but it is a way of getting to this, say if we're doing something more complicated in the future, and this was not the objective to be skilled at. And always as a reminder, you don't get to use these things in college. All right, so that is it. I'll get this posted. And if you ever run across a word problem, the word problems are just these are in disguise. All right.